Hello everyone. Today we discuss limit theorems. They are basically modified versions of corresponding statement for sequences. Remember, a sequence is just a special function. So the theory of limits of sequences can be extended to a theory about limits of functions. That's why limit theorems for sequences also have analogous versions for functions. In this section, I'm gonna state several statements for functions and then recall corresponding statements for sequences. Hopefully, that gonna let you see the similarities and also differences between these statements. The similarity is expected as explained earlier. The difference comes arise from the reason that we need to modify the statement accordingly to study functions, which is a somewhat more complicated object. We start with the following theorem. Recall that a convergent sequence is bounded. So for a function, we have the following result. If f has a limit at x approaching c, then f is bounded on some neighborhood of c. That is, there exists a delta neighborhood of this point c such that for x in a 0 smaller than the absolute value of x minus c smaller than delta, then fx is smaller than m for constant m. So this is the corresponding statement for function. And we see it has some similarity, but also some difference in comparison with the statement for sequence. It is admittedly a little bit more complicated, but the proof, as you see here, is basically the same. Let limit of f when x approaching c equal to some number l. Then we choose epsilon equal to 1. There exists some delta bigger than 0 such that for 0 smaller than x minus c smaller than delta, then fx minus l is smaller than epsilon, which is equal to 1. Then for x in this neighborhood of c, fx is going to be equal to fx minus l plus l, which is smaller than or equal to fx minus l in absolute value plus l. So this is the triangle inequality. But the difference fx minus l in absolute value must be smaller than epsilon, which is equal to 1. So together, this expression is smaller than 1 plus L, and we can choose this 1 plus L to be the constant M, which bound the function over this neighborhood. Really, the essence here that this number M doesn't depend on the choice of delta. Now we're gonna state a few statements about the compatibility uh, a limit of function and algebraic property. So these statements again are very similar to corresponding statements for sequences. Part A says that if the limit of fx equal to L and the limit of gx equal to m when x approaching c, then the limit of f plus g gonna be equal to L plus m. The limit of f minus g is equal to L minus m. The limit of f times g is equal to L times m. The limit of b times f for some constant b, this is going to be equal to b times L for some constant b. So essentially, here it says that we can interchange these operations, the limit operation and the algebraic operation. You can, on the left hand side, you take the algebraic operation first, f plus g, f minus g, f times g, and so on, and then you take the limit later. On the other side, you take the limit first to obtain L and M, and then you do the algebraic operation on these numbers L and M. That's why it's called compatibility results for the limit and algebraic operation. Now, part B is about division. And here we have to be a little bit careful because we don't want to divide by 0. So the assumption here is that if the limit of some function f of h when h approaching c here equal to h different from 0, then the limit of the ratio f divided by h equal to L divided by h, capital H. Again, the next statement is about the compatibility between the limit of function and order property. The first theorem says that if a smaller than or equal to fx smaller than or equal to b and limit of f of x equal to L, then immediately the order is carried through to the limit. That is a smaller than or equal to L smaller than or equal to b. We also have squeeze theorem for function. If fx is smaller than or equal to gx smaller than or equal to h, and the limit when x approaching c of the smallest function fx equal to the limit x approaching c of the greatest function h of x equal to some number L, then the limit of the function which is sandwiched in the middle is also equal to L. So this is very similar to the statement for sequences. Remember, the squeeze theorem for sequences says that if you have sequences xn smaller than equal to yn smaller than equal to zn, and the limit of the smallest sequence xn equal to the limit of the largest sequence gn equal to some number L, then the sequence in the middle yn must converge to L as well. Now, I'm going to give several examples to illustrate how these theorems are applicable in practice to find the limit of a function. First example, sorry for the interruption. Let's go back to the example here. We consider the function fx equal to x squared, and we want to find the limit when x approaching c. Recall that the limit of the function x when x approaching c is equal to c, and we realize that fx here is equal to x times x. That is, essentially, it is the product of two functions, which we know how to find the limit. So we let h of x equal to g of x equal to x. Then the theorem above, the compatibility result between limit and algebraic properties, implies that the limit of the expression x squared equal to the limit of hx times gx, and this is equal to the product of the limit. So the limit of the product is equal to the product of the limit. That is essentially the content of the theorem. And the limit of each function here is equal to c. So that's why the limit here equal to c squared. Now we have another example about the limit of x squared minus 4 divided by x squared plus 1. Here we proceed by a very similar argument. The only point that you should be careful about is that we want to make sure that the denominator here doesn't converge to 0. So we consider the limit of x squared plus 1 here, which is equal to the limit of x squared when x approaching 2 plus the limit of 1 when x approaching 2. Then by the above example, this equal to 2 squared plus 1, which equal to 5, not equal to 0. Just we can apply the compatibility theorem part B above to conclude that the limit here equal to the limit of the numerator x squared minus 4 divided by the limit of the denominator x squared plus 1, which equal to 2 squared minus 4 divided by 2 squared plus 1, which equal to 0. Now, part C here will be a little bit tricky. We consider the limit of the ratio x squared minus 4 divided by 3x minus 6. Again, we check the denominator first, and we see that the limit when x approaching 2 of 3x minus 6 equal to 3 times 2 minus 6 equal to 0. So the theorem above, part B, does not apply. That's why we had to first do some algebraic manipulation to avoid dividing by 0. So we simplify x squared minus 4 divided by 3x minus 6 as follows. This is equal to the numerator here is x minus 2 times x plus 2. The denominator here 3x minus 2. So both sides have that common factor x minus 2. So they can cancel out each other. Then we have x plus 2 divided by 3. So these parts cancel out each other. Then the limit of x squared minus 4 divided by 3x minus 6 when x approaching 2 equal to the limit when x approaching 2 of x plus 2 divided by 3 Now the theorem above, part B, is applicable because the denominator is 3 not equal to 0. So the limit here when x approaching 2 of x plus 2 divided by 3 is equal to 2 plus 2 divided by 3 equal to 40. And this is the final answer. The next example will require you to use, instead of just the comparative result, something else. So we would like to compute the limit of x to the 3 half when x approaching 0. We first observe that x squared is smaller than equal to x to the 3 half, smaller than equal to x, for 0 smaller than equal to x smaller than 1. So by the comparability results established above, the limit of x squared when x approaching 0 equal to 0 times 0, which equal to 0, and the limit of x when x approaching 0 equal to 0. That's why we can apply the squeeze theorem to conclude that the limit of x to the 3 half is equal to 0. The final example, the limit of psi of x when x approaching 0, follows from a very similar argument. We use the squeeze theorem to show that the limit here is equal to 0.